Welcome back to another lesson. Today we are looking at the wave model of light. To start the lesson, we're going to do the following do now question. So we have the absorption spectrum of 3 different types of stars, and we want to order the stars in their velocities from the fastest to the slowest in terms of their perspective speeds to the observer. So number 3. That is the one that's moving fastest. Then we have our second one, and then we have our slowest one. Now, just to explain what we mean by this, as you can see, if I just draw this out, so although in this particular absorption spectrum, number 1 here, although the absorption band is a bit closer to 700 than the one we have in scenario 3, you can actually see that in scenario 3 there is no absorption in the blue spectrum of light. So what that indicates to us is the object is moving further away from us. So we have our stationary observer, and then we have a star, and that's moving further away from us. According to the Doppler effect, we should see a longer wavelength, hence the red light coming through here. Okay, so we see the red light coming through. The slowest one has a lot more absorption in the blue spectrum of light, and so what we can see here is for this particular star, the star is actually moving away slower compared to the star we have in number 3. So what we're looking at today is just looking at what diffraction is and how diffraction affects light. We're going to be discussing this particular dot point. We're going to conduct a little analysis, a qualitative analysis of the diffraction of light. So let me define these two terms, diffraction and interference. Diffraction, deviation of waves around obstacles or through apertures. Interference, two scattered waves that interfere constructively or destructively, forming dark and bright regions or lines. Okay, so when something is interfering constructively, this is what we call it, two waves coming in phase of each other. So two waves that are coming along, and they are basically identical in where the peaks are and also where the troughs meet. Now, when we say in phase, it doesn't mean they have to arrive at the same time. It just means the orientation has to be the same. So this could be in the same wavelength, so we can say it's 0 degrees in phase, or it can be 180 degrees out of phase, or 180 degrees in phase. So instead, let's say this wave doesn't meet side by side. Instead, it meets a bit later. So one wavelength behind, like so. Okay, so about 180 degrees behind that. Or we can say this is one wavelength in total. You can see the minimum point and the maximum point still align with each other. And so you still get waves coming in phase with each other. You still get constructive interference. Okay? So that's what we mean by in phase and constructive interference. Destructive interference is when the waves are completely out of phase with each other. So what we mean by completely out of phase, we're saying that the waves do not match wherever the maximum point is for one wave. The opposite wave is at its minimum point, and when it's at its maximum point, it reaches the minimum point of a different wave. And following suit like so. And what happens is when you have, let's say this is +1, the aperture is +1, and this is -1, comes down here. Obviously, +1 -1 gives you an overall net displacement of 0. And so that's why you see dark bands for destructive interference waves because they basically cancel each other's magnitudes away from each other. We talked about that for sound in Module 3 in Year 11. We're also talking about this, but in terms of light, in Module 7 for Year 12. So what we're looking at here is diffraction and interference as a qualitative analysis. So we're going to look at certain properties of diffraction and we're going to try and understand what's actually happening here. Okay, just for a little bit of interest's sake, we'll get to this in Module 8 as well, but we know that light at this point in time, back in Newton's time, was thought as particles. Some arguments were for waves. Now, to explain diffraction and interference, the wave model is usually the easiest way of going about it, because we know that you can really explain how waves kind of deviate from a particular point. You see your hand. If you put your hand underneath a bright light, and you will see your shadow. Now, the blurry bits that you see is the form of diffraction and interference. Okay, so the reason why certain blurry points are or why you see blurry points is because light is being diffracted into multiple directions. If you looked at it even further down, you'll see something slightly more different. Okay, you'll see these little patterns where things are not as clear. You might see some bright bands, you might see some dark bands if you look down really closely. So that's also showing the interference patterns just using your hand and a bright piece of light. The image I have here is just an ink paint, so we know that ink is just made of particles. And when we have particles, we should really see a very defined edge, because particles can't technically deviate from a particular point. So if I had some kind of layer boundary here, and I have some kind of ink gun, dot 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 goes through here, or gets blocked off here. If I had ink coming through here, dot dot dot, it comes down. So you get a really distinct line point of the image. But what we do know is that electrons, they're considered particles, but they also produce diffraction patterns. We talked about light being, waves, wave-like properties, and it diffracts. So one of the interesting things is we soon realize that particles actually also have wave-like properties and diffraction patterns. But we're not looking into this today. We're more looking at this in terms of the context of light waves. So what properties do we know about diffraction? Well, firstly, we know that if you have a wider opening, so this particular opening here, you have less diffraction, or wider openings here, sorry, this one here. Wider opening, you get less diffraction. You can see diffraction comes around here. Okay, if you have a more narrow pathway, you have a much wider diffraction point. If you have a greater wavelength, you have greater diffraction. If the slit width is greater than the wavelength of the wave, you get these things called nodal lines formed. So points at which you see zero sort of movement. Okay, so zero movement points there. So the person who actually explained this model of light as being waves was a guy called Christian Higgins. Now he came up with the idea that each point on a wave is just an old wave point. Okay, and at that wave point you get a new creation of waves, and if you sort out the sums of each peaks of the wave, you get this nice little line in which we now call the wave front. So that's his idea of how waves are formed. You have one old wave front that acts as a point source, and then you have these curves, these waves that expand like a circle in all different directions. And if you assume the sum of all those wavefronts, or all those new wavefronts, you get this line wavefront here. Okay, and so we have the formation of the diffraction pattern. Okay, so when diffraction patterns occur, each point acts like a little point source that keeps the wave moving forward. Intensity of the diffraction pattern, we can represent it like this particular curve here. And so let's go into that modeling. Let's have a look at wave diffraction. So I have here a light generator. I have the slit with a separation distance of 500 nanometers. And I'm just going to simply run through what happens here. So I'm going to have a screen, and on my screen it's also going to show the intensity of light. So let's just rock and roll, and we have sort of green light coming through. So you can see the wave coming through. It hits the little obstacle, and now it's diffracting out into a particular direction. You can see what's happening here. We have the brightest band in the middle, so the highest intensity, and you can see a gradual little drop off along the two planes. Now there's a couple of things we need to have a look at in terms of diffraction. We want to firstly look at the effect that the slit width has on the overall diffraction pattern. So let's say my slit width is now increased. Look at what happens to the intensity or the diffraction of our pattern here. So I increase the slit width to the very maximum point, and you can see that there's a greater intensity in the center now, and we don't have as much diffraction of light across the entire screen. As a matter of fact, it kind of just drops off and goes to almost zero on these two sides. It does pick up on later on in the other side of the screen, which we don't see, but you can see that's what's happening here. And if I just minimize that, you can see the whole intensity. Now, what would happen if I reduced the slit width? Let's go to the very minimum point. And you can already see the diffraction pattern from here is already different. You can see it's diffracting in a greater range. Why do I say that? Well, you can see on my screen, I can't actually see the intensity bars anymore, and you can't really see that on the little intensity screen here. So if I just brighten that back up, you can see it's kind of like a little, curved or little deviated line like so. So you can see by decreasing the slit width between these points, there is a greater diffraction or movement of light passing through. Let's try and test this with a longer wavelength and also a shorter wavelength. So let's look at with red light, what happens here. So according to the formula we're going to look at soon, if you increase the wavelength, you should see a bigger, diffraction point. So you can't really see this as clearly, but maybe if we were to increase the slit width and just try and compare to the maximum point here. Okay, so you can see even in comparison to the green light, it is slightly more diffracted at maximum slit width. And let's try the shorter wavelength, which is blue light, and in this one you should see a lot less diffraction. So you can see here with the shortest available wavelength, we have a much higher peak in the center point and a lot less deviation along the slit after it's passed through. So that shows us that by increasing slit width, you effectively reduce the diffraction. And if you increase in wavelength, you increase diffraction. Increase in slit width, you'll decrease the amount of diffraction occurring. When you're changing the slit width and also the wavelength of the actual wave. So more diffraction will occur if the slit width is small, and more diffraction occurs if the wavelength is long. And so we see that as well. Okay, you'll see diffraction patterns in all sorts of parts of life. If you look at the old CD, it's just made of really tiny little slits that split up white light, and that's why you get the whole spectrum of the rainbow forming there. One of the famous applications of diffraction was the discovery of the structure of DNA, where Rosalind Franklin used X-ray crystallography to bombard a crystallized DNA model, and those bombarded diffracted rays then hit a film that fluoresces, and the image of photo 51 occurred. Now, as you know, with the little demonstration we did with the PhET simulation, we can come up with a little explanation or little formula pattern to explain diffraction patterns with the slit width and the wavelength. And this is what we come up with. Now, if we try and understand this equation here, okay, we're saying diffraction is proportional to the wavelength over slit width. Another way of saying it, let's just say diffraction, we call it D. Okay, we're going to say diffraction is inversely proportional to the slit width. So as the slit width increases, the diffraction pattern that we see will decrease. If we're looking at diffraction pattern with wavelength, we can see that the diffraction pattern is directly proportional to the wavelength. So if we want to increase our diffraction pattern, all we have to simply do is increase the wavelength of the wave that's going through the slit. Okay, so let's have a look at interference patterns now. So interference pattern, like I said before, it's just when waves either constructively interfere or destructively interfere with each other. What are some properties of wave interference? Well, firstly, constructive is when you have the two maximum points intersect to produce an extra high maximum point or higher amplitude. When you have destructive interference, that's when your maximum point or the crest interacts with the minimum point of another wave and effectively cancelling each other out. And so you have no wave displacement. So this is an example of constructive interference. Two waves arrive at the same point, and they reach the same point in the same orientation as each other. And you get an increase in the overall amplitude of the wave. So the amplitude is increased or doubled, we can say. If we look at deconstructive interference, they arrive in exactly the opposite orientation to each other. And when that happens, you get zero wave displacement. Usually what we do is use monochromatic light when we're studying diffraction and interference, just because with monochromatic, which means the same color, it gives us a better contrast with the bright bands and dark bands, and overall it just makes a lot more sense. Okay, so the next bit we're also looking at is the interference patterns and slit width and separation. Okay, so let's have a look at wave interference with light. Again, we're using PhET. We are using a light generator. This time we have two slits. And we have our little screen and our intensity bar. So let's just run it through at slit width of 500 and slit separation of 1500 nanometers. So click it through, let's see what happens. Okay, so you can see here we have a couple of bright bands in comparison to the diffraction pattern. You can also see that we have a couple of dark bands as well. Okay, when we have some lighter bright bands here. So when we look at interference, we also need to look at what causes a larger amount of diversity in the patterns. We know that by decreasing or increasing slit width, we'll use that example. Increasing slit width will decrease the amount of diffraction. So let's look at that. So you can see it almost forms like that diffraction pattern we had earlier, but that's not really what we're going to try and do in this comparison. We're going to try and do changing this slit separation and see what happens to our diffraction pattern. So if I decrease that separation, okay, it almost acts. So you can see that we have a much broader bright band and much broader dark band. If we increase slit separation to maybe the maximum available here, you can see we actually create a lot more bright bands and a lot more dark bands here. Okay, in many sense, you can say that the clarity or the clarification of the bands are probably a lot clearer to see for an interference pattern than it is for a diffraction pattern or diffraction or a single slit example when you use two slits instead of a single slit. So there you have that. So that's what's exactly happening in interference patterns. You have light that is interfering constructively, and so that's where you get the maximum point. And then you have the light interfering destructively, and so that's where you get the dark points. So let's just quickly recap what we did today. We firstly looked at the wave model of light by conducting some investigations qualitatively on the diffraction of light. We talked about how if you want to increase the diffraction pattern, you have to increase the wavelength or decrease the slit separation, or the slit width, sorry. And we also looked at how diffraction causes interference. Now, generally speaking, if you have diffraction, you will get interference, and so on and so on. Okay? Anyhow, thanks for joining in this lesson. I'm Mr. Wong. See you next time.